Okay, so Mark, what is on that paper? Nice. Okay, so let's continue with what we started on Monday. On Monday, after solving example 19, we discovered that there is something about the mode shapes and the two mode shapes. And again, by mode shapes, what this system naturally would like to do, because of symmetric and everything, there are two modes. One, they like to move left and right together. So the spring in the middle is redundant, and we get rid of that one. So, and then the second mode, we discovered that since the two masses likes to move left and right, but in opposite direction, then we said if you put a camera, the point that I showed by red over there is a node, is a fixed point. So we can cut this spring at that point because now we have two independent systems, right? Somebody asked, maybe I move fast, why it is 4K? Okay, so if we have a spring, right? If you cut it in half, the stiffness will double. Do you agree? Let's say if I have a spring that the stiffness is 4K, and I have another spring that the stiffness is 4K, right? If I attach them together, the equivalent spring you learn, since these two are series, right? 1 over K equivalent is 1 over 4K, 1 over 4K. So your K equivalent will be 2K. That's why when I cut it in half, I put 4K here. These 4K and K, again, they are, this time they are parallel, right? Why they are parallel? Because their displacement are the same. So that's why we add them and we got 5K. So the result, we found that instead of dealing with a 2-degree freedom system, we can convert them to two independent 1 degree of freedom systems. That was the story that we had last day. Now let's do the same things with example 20. So we have two pendulums, identical, the spring in the middle, okay? So these two systems, naturally, if I ask ourselves, naturally what this system would like to do, because there is no difference between the pendulum on the left and right, we say once maybe these two pendulum likes to move left and right together, all right? Exactly the same in a perfect world. So it means the spring in the middle is not gonna have any deflection at all. So it is redundant. And the second mode, this two-main pendulum likes to move left and right, but in opposite direction, right? Swing left and right in opposite directions. So if we put a camera, again, we realize that the point in the middle of this spring is a fixed point. So I can therefore cut my spring here and treat each pendulum independently. So let's write it down here. We'll say mode 1, we're going to have only one spring, only one pendulum, because the two pendulum, they are exactly on the left and right, they are the same. So a pendulum like that one, we know what is its natural frequency. We calculated before, it is G over L. All right, so done. That's the first mode and first natural frequency. And if we want to show the mode, it's going to be 1 and 1. And our definition of the mode shapes, right, the ratio between x1 and x2. Yes. They are moving together, left and right. No, if they move together, it means that you can remove the spring, right? Remember, the goal is to make a 2D coupled system to two independent systems, like totally separated. So let's look at the mode 2. Mode 2, as I said, they are moving left and right, swinging in opposite direction. So I can then convert this system to, let's say, a pendulum mass m and a spring, which I cut it in half, and I fix this point to the wall. So it is fixed. So my stiffness now, it is 2K, similar to previous example, right? So I have a simple system, which I know how to solve. It's a 1 degree of freedom system, and you know how to solve it. Let's quickly solve it. So this is B, and the whole thing is L. What I can write is, let's use Newton. I'm gonna have 2K B theta, and here I'm gonna have mg, right? So if I write the equation, sum of the moment about point O, I O alpha, I have mg L sine theta, 2K E squared theta equal to ML2 theta double dot. You know that this one, right? That's a single degree. You've solved way more difficult problem than this one. Order it, get rid of sine theta. So we'll get ML squared theta double dot plus 2K E squared MGL theta equal to 0. So that's my equation of motion, and simply my natural frequency will be equal to 2K E squared MGL, or I can simplify it. I can write it as 2Km BL squared plus GL. All right, so that's my second natural frequency. And as we defined, our mode shapes for this one is 1 and minus 1. 1 and minus 1 again means these two, the same amplitude, or the ratio is 1, but they are in opposite phase, right? Because we have a negative sign here. Always make sure to check your omega n unit to make sure that the unit makes sense, like always when you solve a problem. All right, so this is, yes. Right. So it is in the middle, right? Yeah. So your question is, if we don't put it in the middle? Yeah. No, the reason that we put it in the middle because only middle is a fixed point. Oh. Why? Let me repeat it again. So that's mode 2, right? Mode 2, what it says? It says these two pendulums are going to swing in opposite direction, right? If they move in opposite direction, the exact same amount, and you put a camera and watch this spring, you will see the point in the middle does not move left and right. Maybe it makes sense for this one. Like here, you have two identical systems, M and M, right? These two M, they go left and right. And do you agree if you put a camera, that red point is not going to move left and right? Do you agree with that? No? So you guys all follow what the logic that we do? Yes. So with mode shapes, we're always before the perspective going into velocity. Exactly. Mode shapes, what would the system naturally like to do? All right. You look at the system and you say, okay, I have a system here. there is no advantage for the one on the left and the right. Everything, they are exactly the same. So you say this is a Pendulum system. What are the possible ways that this system can move? So possible ways that the system can move are either they move together or they move left and right. Do you think of anything else? Anything of anything else other than these two? No, right? That's the only possible way that this system can move. Let me ask you these things. If I have a piece of paper, and this piece of paper, a paper, and this paper, I'm just showing it the cross section, all right? This is the cross section. If I ask you this system, if I want to like excite it, how this system can deform or move. So you may tell me that it's possible that it deform like this. You agree with that, right? It can do like that and that. So what else you may say? Well, you may say it can move like that or like that. That's all possible. What else think it can do? So you can do many of these things, but you may say, well, no matter how I excite these things, it wouldn't be possible that these things can, let's say, no matter how much I excite it, no matter how big the force is, it's maybe highly unlikely that I can get a shape like that. So we call these mode shapes, but that's for a flexible system, right? That's our next topic. The reason that I said that is because with a piece of paper, you can feel what are the natural way if it can move, all right? So if you have, for example, a cantilever beam, let's say you have a steel, maybe a ruler, and you attach it to the desk, okay? So it's a cantilever beam. And so we say if we excite this, the whole base, how this, let's say, cantilever beam can move. So probably you would say it likes to move ups and down like that. That makes sense. Or you may say, well, it may do that, right? That's another way. And the opposite, of course, is going to be that. So it's going to vibrate like that. But I guess you would say it is impossible, let's say, that these things like move like that, right? So we say their mode shapes are like this one, that one, maybe other mode shapes, which we'll discuss them later, but not that one. So the mode shape is the natural way that the system can move, all right? So that's the mode shape. So moving back to this idea, so you have this system, and if somebody asks you, this system naturally, if it can move, what are the possible ways this system can move? You say, well, two possibility is these two systems move left and right, and another possibility they move in opposite direction. We don't have any other choice. Now, between these two, since the one on the left and right, they are identical, there is no advantage for the one on the left and right. So if they move together, right, the amplitude is going to be the same. So that's why you get rid of the spring in the middle. If they move in the opposite direction, right, try to visualize it. If they move in the opposite direction, the point in the middle, that red point, is not moving left or right. So it's a fixed point. Since it's a fixed point, I can use let's say, a nail it to the wall or to the screen here. Okay, so my system on the left and right, they are independent. Make sense, Jenny? Not Jenny, sorry, I mixed you with someone else. Yes. No, forget initial condition. This is the mode shapes, and mode shape is for natural way system can move, all right? Naturally, without any disturbance, without anything. We said, what are the possible way this system can move, okay? So let's get rid of these. We'll get back to this one when we get to the continuous system. Here in this pendulum, again, you have two identical systems. Two possible ways that this system can move is one, these two pendulum swing left and right, but together. That's one possible way. We call it mode 1. Another possibility is these two swing, but in opposite direction. We call that mode 2. And we took advantage of these system being symmetric, and we said, well, if they are moving left and right together, then the spring in the middle is not going to deflect at all. Again, in a perfect world, visualize that also the vibration is small. So I convert the whole system to a two independent, exactly the same 1 degree of freedom system. All right? And this is their natural frequency. Yes. Say it again. Again, because they are exactly the same. They are identical, right? Yeah, we take advantage of symmetry. No, exactly. If the mass here instead of m was 2m, so this method doesn't work. Okay, so far we managed to find then the mode 1 and mode 2 for this one, and this is its natural frequency. All right. You can do this one as an example later, as a practice. I'll leave it for you to practice. Obviously, that's very similar to the previous one, but figure it. Now, this is where probably you've been waiting, and that's what if the system is not symmetric, okay? Or you may not like that trick for the motion. You want a systematic way to decouple your system, all right? Look, I want your attention for 10 seconds so you know what you're going to do, because the rest is going to be just all math. So moving one step back, with the two examples that I just solved, what happened with them? We had coupled system, a 2-degree coupled system. We turned them to two independent systems. Why did we do that? Because with 1 degree of freedom system, it is easier to deal with. We know how to solve their equation if they have, for example, external force. That's better. Our goal here is to convert an n degree of freedom system to n independent system. All right, so here is the goal. Making an n degree of freedom system to n independent 1 degree of freedom system. So we were lucky with like a system like this one because it was symmetric, it was 2 degree of freedom, and we intuitively could figure how this system moves. But what if the system is not symmetric, like this one is 2m, or maybe the length of one of the pendulum is longer, or maybe if the system is 3 degree of freedom or 4, then that's not possible. So here is a systematic approach to make the system like making an n degree of freedom system to n independent system. So this is how it goes. I'm not going to go through the proof. Proof is in your textbook chapters, the second chapter that you have, or chapter 7 of that book that I picked. You don't need to study that for this course, only if you are interested. I'm just going to go through the procedure. Okay. So we have our equation, and this equation may have also an external load, Ft. Okay. So far, no damping, but I just added an external load. So that's the whole thing. First step, you will find the natural frequencies. we used this equation before, and we know how to find the natural frequencies. Okay, all right, so I have my matrix K and M, and I find natural frequencies. Then the second step, we will find the mode shapes. In order to do that, you learn that you can find the ratio of x1 to x2, right? It can be a number, which you found. Right? Going back to the example that we solved before, so you have natural frequency of 1. I'm going to move back. I forgot the numbers. It was this one, or yes, this one. 618. So what was the natural frequencies? Km. And okay. So you solve this one, you will find the natural frequencies, which for that example, we managed to find that the first natural frequency is this, and the second was 1/618 square root of k over n. Second step, you will solve this algebraic equation, and from that, you find the ratio of x1 over x2. So the ratio of x1, x2, when it is omega 1, we managed to find that number to be 618. And when it is omega 2, that number was -1, 618. All right, so the example that we solved before, yes. I'm going to get to that in a moment, yes. So from here, what happened? You showed it as x1, your first mode. We showed it, we agreed to show it like that. And we show it as 1/618. And the mode 2, I repeat these things. I just want to make sure that you understand all the steps. So since we have the ratio, we put one of them equal to 1, and we managed to find the other one. All right? So we call them mode 1, mode 2. Now, what if we have a 3-degree of freedom system? The same. We will solve this equation. So you will find x1 over x2, it gives you a number. x2 over x3, it gives you a number. All right? You set the last one equal to 1. Right? So x3 is equal to 1. So you will find x2. If you have x2, then you can find x1. All right? And you will show all of them in a vector format like this one. As you can see, the last one is equal to 1. Okay? So whatever we did here in this example of 2-degree of freedom system, now we are going to do it for n-degree of freedom system, but in a systematic way. So in a 2-degree of freedom system, you recall we found the ratio, then we set one of them equal to 1, and we found the other one, because we said we only have access to the ratio, not the actual amplitude. Right? Doesn't matter. If you have an n-degree of freedom system, you put the last one equal to 1. Let's say if you have a 3-degree of freedom system, you will find this number, x1 over x2. You will find x2 over x3. All right? So you set your x3 equal to 1, and then you manage to find x2 and then x1. All right? So you show them in a vector format. For example, for a 3-degree of freedom system, your modes are going to be a number, and 1. And that's your mode 1, and so on. Because remember, you have now 3 natural frequencies. So the same things for mode 2. You have 1, some numbers here, and mode 3. The last one is equal to 1, and you have some numbers. This comes from omega 1, this comes from omega 2, and this comes from omega 3. So far you guys are with me? Okay, any question? We haven't done anything special. The same things that we had, we solve this determinant, which we did before. We find the natural frequencies. We solve this algebraic equation. We find the ratio of x1 over x2, x2 over x3, and so on. We set the last one equal to 1, and we find the rest of them. We show them in a vector format. All right. So this is our mode shapes. Right? This is what we call them, mode shapes. Now, just to tie them up, we will put all these columns next to each other. So this is U, a big matrix. Each of these columns is the mode shapes. And we call that one the modal matrix. That's a name somebody picked before, and we use it. The mode shapes, we put them in a matrix, and we call it a modal matrix. All right, so now here is the actual magic. This modal matrix, if we use it in this format, it will transform our coupled mass and stiffness to a decoupled system. And this is what we wish to have, all right? And they will be all diagonal. Remember when I showed you the matrices, I said, well, they are not diagonal because they are coupled, but if we transfer them to these new matrices, which will show them by MD, means mass diagonal and stiffness diagonal, they will be diagonal. So, few things. This converting comes from that we replace our original coordinate system, x1, x2, and xn, to y coordinates. And those y coordinates, they came from this transformation. X is equal to uy. So there is a lot of missing things here. You may ask why they are decoupled, right? So that's all the math that prove it. But in a simple way, if I want to explain it, if you show this result to a mathematician, the moment they look at, maybe you should stop here and listen, then we'll continue with the rest. The moment you show to a mathematician these two formulas, like this one and this one, what would they say? Don't tell them that K is a stiffness, M is mass. Tell them that K is a matrix, M is another matrix, and I put them in this equation, and I got some numbers for omega, and I put them in the second equations, and I found like a vectors like that. What would they say? Alberto? Exactly. Thank you. So if you show these two matrices, don't tell the mathematician that they are a stiffness, they are coming from a physical system. Tell them that you have two matrices. They are a square matrix, K and M. All right? Some arbitrary numbers. If you put them in these two equations, immediately they will say that's the definition of eigenvalues and eigenvectors. So your omega squared here are the eigenvalues and these are the eigenvectors. I believe in your past courses in algebra or math 101, 102 somewhere, you learn about eigenvalues, right? Hopefully. And eigenvalues and eigenvectors, or in other words, eigenvectors for a mathematician means the principal coordinate. But for somebody who analyzes vibration, the eigenvalues are the natural frequencies. Eigenvectors are the mode shapes. And that's the beauty of like math And here, because here we have like a purely mechanical system, right? And we solve the equations. At the end, we found that the eigenvalues of this system are the natural frequencies. So anyway, going back to the mathematician, they say they are the principal coordinate, and with the principal coordinate, it means if you use this conversion, like transform your x to u using this u matrix, which u are the eigenvectors, it means you're going to get independent equations. So that's why, but the whole proof is in your textbook if you are interested to know why they become decoupled. We'll just use them, all right? So if you've heard somewhere again, this y variable, now it is called principal coordinates. All right, what else I need to tell you here? Now let's put them all together. So your original system, which was a coupled system, will turn to a decoupled system because MD is decoupled, KD is decoupled. But remember your variables now, they are not X, they are U. It was our original system, M X double dot T, A xt equal to ft. It was our original system, but our original system, they were coupled. Coupling means x1, x2, they are into each other, they are interconnected. We don't like that one. The new system, this guy is decoupled. So we are going to end up with separate equations, each of them a single degree of freedom system, which we can easily solve them. Don't worry if you don't still follow, I'm going to solve one example and we do all of this step manually. So you will see it's not really that difficult. So in case you have initial conditions, remember we are changing our system from x1, x2, and so on to y1, y2 to a new system, new coordinates. Our initial condition will also change. After you solve your equation, so obviously you're going to get the answer in y coordinate. You like to go back to your original system. So you transfer back everything to your original system. Okay, so that's all the steps, but I will show them to you in an example. You'll see it's very easy. And everything comes from this U matrix, the mode shape matrix or the modal matrix. And this modal matrix is the eigenvectors. So by shows of hand, tell me if you've heard eigenvalues and eigenvectors before. Okay, good. Have you used them before? Like anywhere in, no? You haven't used them at all, right? So I remember when I read about, like when I study eigenvalues and eigenvectors, two things, which I thought they are the most useless things to learn. One was eigenvalues and eigenvectors, and the second one was Fourier transformation. And because my math teacher, he was really tough and gave us really hard time. And always I hate, like I said, why do we need to learn this? Because we're not going to ever use them. Gave us like big matrices to find the eigenvalues and eigenvectors. I said, who cares? And the same with Fourier transformation. You remember Fourier transformation, right? Hopefully, some of you studied all those integrals. And later, when I started working in the lab, which I did vibration analysis, I realized without Fourier transformation and without eigenvalues and eigenvectors, that lab will be closed. Like you cannot do really anything. So there are applications. You will see one here, the eigenvalues and eigenvectors. The eigenvectors give you the mode shapes or the U matrix, and the eigenvalues gives you the natural frequencies, right? So Let's solve one example together, step by step, and see how we can use actually all these steps that I showed you. You'll see how easy it is. Again, I'm going to do it with a 2 degree of freedom system, because even with a 2 degree of freedom system, it is a pain finding the eigenvalues and eigenvectors, which I did the calculation before coming to the class to save some time. Okay, so step number 1, you start with always the equation of motion. That's the easy part. All you need to do, draw the free body diagrams, or if you are doing Lagrange, you use Lagrange. All right, so I have one here, one here. So this question, we also have external force. This is F2 and this is F1. This spring is going to be K1, X1, and these two are going to be K2, X2 minus X1. Free body diagram. The Newton law, step 1, equations of motion. So you will do the Newton law, sum of the force, M, X double dot for the first one, M1, X double dot 1. So I would get K1, X1 plus K2, X2, X1 plus F1 equal to M1, X double dot 1. So we will do that for M2, X double dot 2. So what do we have? We have K2, X2 minus X1 plus F2 is equal to, not 0, M2, X double dot 2. We will order them, put them in a matrix format. So we are going to have, and let's just substitute the number that we have. 0, 0, 20, X double dot 1, X double dot 2, plus 200, 100, minus X1, X2, oh, I need room. Is equal to F1, which is 5 sine omega t, and this one just sine omega t. So this is our step 1, the equation of motion. So we discussed how you can quickly check to make sure they are correct. So your mass matrix is decoupled here in this system, 30, 20, so correct. Your stiffness matrix, sum of the stiffness and so on. And off diagonal, they are negative, so it seems everything's to be correct. These equations, they are coupled. At least one of them is coupled. And it causes problems. It means when you write the equations, you are going to end up with the differential equations, which they are coupled. So that's why we are going to go through the trouble and find the U matrix. But we are going to do it once, just manually. Step number 2, find natural frequencies. So simply, you know, the determinant of matrix K minus omega squared M equal to 0. So it will give you the first natural frequency, which is 5/3, and the second natural frequency, which is 10. I did the calculation, but you know how to do that. Step number 3, find modal matrix. By modal matrix, we need the ratio of x1 over x2. So you need to solve matrix K, omega squared, matrix M. Let me not write the matrix. K, omega squared, M, x1, x2 equal to 0. From here, you will find the ratio of x1 over x2 and x1 over x2, which is 0.6667 and minus 1. So the ratio. So when we have the ratio, we decided to set the last one. Here we have only two, 1, and then show them as our x1 will be then 1, and this one 6667. X2 will be 1 minus 1. Okay. So your modal matrix, you'll just put them in a column. That's your modal matrix. That's the most important part for this system. This is what makes our system independent and do a lot of work with that. All right. So at any part, if it's not clear, please let me know. It's important to understand what's happening, so we'll do that one. It seems so far nothing really special. We managed to find the natural frequencies, we managed to find the ratio, and use those numbers to find the modal matrix. The rest is just some writing equations and algebra, nothing special. So step number 4, we need to find MD, which is UT original M U. By T, I mean transpose. Oh. Up or down? You're behind, right? Okay, I'm going to give you time to take notes. Remember, later you will just use one line of code in MATLAB or in Python. You will just write down eigenvalue of K and F, and it gives you U, and it gives you everything. That's what I put in your notebook, which you're going to check it. But believe me, it is important, at least one example, to understand all the steps, see how hard your computer works to give you this number. And you will see the pain even for a 2 degree of freedom system. And let alone if you have, let's say, a 7 degree of freedom system, which is for your project. You don't need to do it by hand, by computer, but for a 2 degree of freedom system, you need to understand all the steps, and you need to see what's actually happening. All right, one time at least. And of course, one time in your exam. So we managed to find U. Now that we have U, we have these two formula that we expect them gives us the two matrices that they are diagonal. That's what we expect, right? That's what hard work that we did. And here is something that I have to admit. Today, when I was doing this calculation, I forgot to put this transpose there. So I found this U. So this is also good for your exam. And immediately I said, okay, MD U, without writing the equation, I put the U matrix, the M matrix, and again the U matrix. I didn't get, of course, the, Oh, that's M. Sorry, that's K. Thank you. So I did that one, but I found a matrix which is not diagonal. Like there were numbers here. I checked and checked and checked the equations, and I thought, okay, I discovered something. Maybe I can win a Nobel Prize. There is a system that this one doesn't work. So for 200 years, people are making mistakes. Then I realized, oh, there is this UT here. So don't forget that. Okay, so because it works, if you use this U, you will get your MD is going to be 55.5600500. And your K matrix is going to be, oh, sorry, this is K. This is 33.34, and this is 50, and this guy is 55.5600500. So two matrices which they are diagonal. And we like diagonal matrices because it means two independent equations. So we will put them in our formula. MD y double dot 1, y double dot 2. Remember our coordinate now are y. AD y1, y2 equal to U. Let's check the formula again. Also here, remember, we have a transpose things going on. Right? UT. I emphasize that because you're going to have one question in your exam, and if you miss with just one transpose, you're going to feel like me that you need to win the Nobel Prize. Right? So it is all matrix multiplication, which you can do and let's do that. So if you put MD, you're going to get 33.34 plus 55.56. This is y double dot 1. Y is equal to 4.33 sine omega t. And the second one will be, so that's my M. Yes, 50 y double dot 2 plus 500 y, this is 1, 2, is equal to sine minus 4 sine omega t. Just a lot of calculation, obviously, but it's not really complicated. So look at these two equations. They are two separate equations. Something that we are familiar with them. We solve similar problems, right? To remind you, we have like M y double dot plus ky equal to f0 sine omega t. And you know how to solve this one, right? You have a formula to solve this one. Let me write it on the corner. So when you have like mx double dot plus kx equal to f0 sine omega t, you know the response of this system is f0 over k 1 minus omega n squared sine omega t. All right, so it means you can find y1t, and you can find y2t. Now that you have y1 and y2, simply your x1t, x2t, that's step number 5. Putting everything back is, so moving one step back, making sure about the formula. It's u, not this time u transpose. It's u y1t and y2t. So you managed to find the response of this system, right? Which was a forced system. It has sine omega t in it by transferring it to a 1 degree of freedom system. All right. So please complete this one and try to get a sense. By sense, I mean, now here you have a U matrix. That U matrix shows you the contribution of each of these modes. Right? Because you will see the actual response of this system, x1t and x2, is combination of these modes coming from y1 and y2. Please complete this calculation. I will review it on Friday for 5 minutes again, explain an extra things to you. And this is actually all we need to know about n degree of freedom system. Our next step is just adding damping to the system. If we add damping to the system, we are done, right? If we add damping to the system and we can convert it to a 1 degree of freedom system, it means we can solve any n degree of freedom system which is damped and under external force. Thank you very much.
Yeah, so this one is the principal coordinate.
That's correct.
So how can we visualize it?
No, you cannot visualize.
Yeah.
It doesn't have any physical meaning.
Because in yesterday manual class, you
Right.
say in PSE you can